Hello, everyone. Hope you're having a good day. To whoever is watching this, be it Sishkanoja or any other student who's watching this, my name is Abdullah Al Sheikh, and today I'm going to do a presentation on FRET. And if you can tell by my title, lights, camera, interaction using FRET as a tool to capture protein-protein interactions in cellular pathways. Now, very simply, what is FRET? To put it quite simply, it's this interaction between two small molecules, usually proteins, but not necessarily proteins, in which we can measure it via the photon emission of these two proteins. If we can excite the first molecule, let's call it the donor molecule, and this molecule can exhibit this photon, it can emit this photon. And if the other molecule, let's call it the acceptor molecule, is close enough in distance to it that it can also emit this photon. And we can tell that the interaction between these proteins has occurred. That simply is FRET. Seems quite simple enough, isn't it? Okay, let's delve a little bit deeper. So how does it work? The principle is very simple. Like we already discussed, the proximity, you want it to be within 1 to 10 nanometers of each other. That's the distance you want. And we can excite the donor molecule, and then it will emit the photon that we need. And then the acceptor molecule will be excited, and then it will emit the photon emissions. So we can almost observe 4 valley peaks, one for each donor and, 2 for each donor and acceptor molecule, one for the photon excitation and one for the photon emission. And once this donor has enough energy, it will transfer its energy onto the other molecule. Now, of course, FRET stands for Forrester Resonance Energy Transfer. So how do we measure this FRET? Well, quite simply, like we've already established, we can emit light via the excitation of the initial molecule. However, there is a contingency. What is this contingency? As we see in this kind of gray area, there has to be an overlap of the wavelength, meaning the emission wavelength of the donor molecule has to be the same as the accepting wavelength of the accepting molecule. As you can see here in the third part, or part C of our graph, the FRET efficiency, we can see this kind of small valley in between the orange and the blue molecule. That valley is the valley of the connection between them. This is the overlap between these two molecules. And this also shows us a very important thing. The FRET efficiency decreases as the distance between the molecules increases. There's an inverse relationship here between the distance between the molecules and the efficiency of the technology. Here we see a CY and a CY3 and a CY5 pair. This is a very common pair. It means sulfocyanine. And this is the equation by which we measure the efficiency of the FRET. 1 divided by 1 plus R, and R here stands for the distance between the molecules, and the RO stands for the Forrester radius, at which 50% efficiency of transfer occurs. Now, like we said, there's an inverse relationship. As R increases, the E decreases. And as E increases, the R decreases. So what is the components at play here? Well, like we already explained, there are 2 molecules, the A molecule and the B molecule. Here we see 2 very common fluorescent proteins, the cyanine fluoroprotein and the yellow fluoroprotein. And this is exactly the thing we were previously discussing, the overlap. The photons emitted by the first molecule have to be in the same wavelength of the other one for our technology to work. If we only see emission from the first molecule, then we know that our technology has failed and FRET has not occurred. Our complex hasn't formed. But if we can see both of them emit, then we can tell that the overlap has occurred and the complex has formed. So this is all great and well. We can study the interactions of proteins or other small molecules. However, what does that mean to us? What do we use it for? Here on the graph on the left, we can see a real-life application of FRET. In this study, they wanted to measure the catalytic activity of the mitogen protein kinase, as you can see here in the green. And the rationale behind this design of this sensor is very clearly outlined in the B part. When the sensor is unphosphorylated, the FHA1 has low affinity for the substrate domain. And the ratio of the YPET is simply just the fluorescent, and turquoise GL is also just another fluorescent. Turquoise GL is the one that's bonded to the kinase, and the YPT is the one binded to the binding domain. So if there is phosphorylation, however, we can easily see an emission from the YPET because the FHA1 will have affinity for the substrate domain. However, if phosphatase removes the phosphate group, it will return back to the original state where we can only see low levels of emission of the YPET in comparison to the excitation of the turquoise GL. The EV linker, for anyone wondering, is simply just to make the distance between the kinase and the binding domain shorter to allow for FRET to take hold. Very simply, the removal of the phosphate group from the sensor will cause the sensor to return to the state where the emissions are low, and the sensor therefore provides a readout of the balance between the competing activities of the kinase and the phosphatase. This allows us to recognize the pattern of the pathway. Another example here is the figure on our right. In the figure on our right, we can observe the difference between these two protein molecules. This protein complex, we can see the PRL2 protein, which stands for phosphatase of regenerating liver. This particular protein binds to this protein CNNM3, which is the cyclin M family of magnesium transporters. This family of protein, of this member of this family of proteins, has this particular domain, this CBS domain. In this CBS domain, we have this particular sequence. Now, it seems very complicated, but it's all quite simple. This particular sequence is very important to the complex formation. If we were to create a mutation in this D426A sequence, then we would prevent this complex from forming. Now, you would say, why would we prevent this complex from forming? If PRL2 were to bind to the CBS domain of this protein, then it would promote tumor growth. As we've previously stated, PRL2 is for regenerating liver. The liver is a regenerating organ. Therefore, if there's no check marks, if there are no checkpoints, it could regenerate onwards and onwards and onwards till infinity. This is quite toxic to the body. Therefore, we would like to inhibit it. How would FRET come into play here? If this complex is forming, then the cyanine fluoroprotein of this PRL2 would be excited, and it would transfer its energy onto this YPET, which is another yellow fluoroprotein of this particular protein of the magnesium transporter family. It would emit a particular wavelength. If we can see that only the cyanine is emitting, that means that we've successfully mutated this sequence and inhibited this complex from forming, therefore prevented future tumor growth. This is especially important as a novel method of treating cancer. This has been tested on mice, and in mice that were had the CNNM protein, CNNM4 and 2, they were deficient in magnesium. However, no oncogenesis was observed. Therefore, we were able to prevent tumors from forming. Now, this is all great news, but what convinces me to use this particular technology over other technologies? One of the most difficult things we have to do as scientists is decide which particular tool we use for each experiment. What do we need and what is most important? These are the advantages of FRET compared to other common technologies that we use in our field. So it's non-invasive. As we are able to view the proteins while they are still live, we do not have to kill them or denature them as in SDS page. we can view them without fixating them. This also ties into the real-time measurements, as we can view them live with much quicker results than if we were to fixate them like a X-ray crystallography. Yeah. This also is super important and comes into play with its comparison to BRET. Now, BRET is very similar to FRET, but it stands for bioluminescence resonance energy transfer. BRET is more useful when studying long-term. However, in the short term, there's more background noise in BRET, so there's more different signals emitted. So it's not as accurate as FRET, and FRET is more sensitive. So we can view it with much more clear, crisper pictures and tuning out the background noise. And of course, it has a much, much higher resolution than your average light microscope or even electron microscope, which might have a higher resolution. However, we would still have to fixate the protein. So it gives us the advantage of high resolution without having to fixate our protein. Now, of course, FRET has some limitations, as do other technologies. It is size dependent. We can only view very small proteins and molecules. And the distance has to be very close between the two proteins. As we've previously established, 1 to 10 nanometers is the sweet spot. That is the range that we want. Even though it's very crisp, we can get it without background noise, there is still some background noise that is visible, and the signal is still considered weak, as it can we can only see it for a flash, but not very clearly. Sometimes still some background noise is visible. And of course, there is the orientation problem. It is orientation dependent. If the orientation of the proteins is wrong, we cannot form our complex. Therefore, we cannot observe any emission. In conclusion, FRET is a powerful technique for studying molecular interactions in living cells. It can be used in a variety of ways to study protein-protein interactions, even protein-lipid interactions, nucleic acids. It's very useful in our field. It has a wide range of applications. And I hope you enjoyed my presentation. Here are my references. Thank you so much for listening to me, and have a good day.